Hey guys, welcome to another Edexcel Further Pure 1 revision video. Today we're taking a look at reducible differential equations. So this brings us to the very end now of the Further Pure 1 textbook and the very last chapter. So quite a bit of a mixed chapter. Some of it can be very, very tricky. Some of it can be, quite straightforward. But it is a pretty brief chapter, so let's just jump straight into it and see what we've got for today's video. So the first question here is a pretty standard kind of exam question. So you're given your variable here, so z equals y to the minus 2. So this is the substitution we're using. And what we want to do essentially is transform this differential equation here into this one here. So if we have a go at this, let's see what we get. So question 2a. So we've got z equals y to the minus 2. So the first thing I can do is basically rearrange this so it's in terms of y. So how would I get that? Well, hopefully it's pretty straightforward. To get this just in terms of y here, this y obviously needs to be a power of 1. I'll have to times both sides here, or raise both sides to a power of minus a half. So that just gives me y, and then my z here, if you raise it to the power of minus half, you're just going to get z to the minus a half. Okay. So the first thing I'm going to do is I'm going to differentiate this here, this dy by dx. Because what we want to find, obviously, is use this substitution here and then put it into what we'd call equation 1. So that's the dy by dx plus a half tan xy is equal to minus 2 sec x y cubed. So if we have a go at this now, so dy by dx, dy by dz, dy by dx, what am I doing? So this is minus a half. So obviously you're going to have to differentiate this implicitly because this is in terms of z. So what it would give you is minus a half z, and then subtract 1 off the power, so minus 3 over 2. And then obviously it's going to be in terms of dz dx. Okay, so that's our dy by dx. Obviously that's what we're using in that first equation at the top. So we've got that now. Now that we've got that, all we can do is we can just substitute into what we'd call equation 1. So dy by dx, we've got that here. So we just write everything out in full and then we'll start simplifying. That's minus a half z to the minus 3 over 2 dz by dx. We have half tan x times y. So we can't do anything with the tan x over 2, but we're timing it by y, and we know y is equal to z to the minus a half. So we can write that as plus a half tan x times z to the minus a half, like so, because that's just what y is. And finally, we've got this is equal to minus 2 sec x y cubed. And y cubed would just be raising both sides here to a power of 3. So if you raise that to a power of 3 here, you just multiply the powers, so just kind of your basic rule of indices. So we're going to get minus 2 sec x z to the minus 3 over 2. Okay, just raising that power there to 3. So now, at this stage here, all we need to start doing is just simplifying. So the first thing I'm going to do is I'm going to get rid of this minus a half here. So essentially, if you divide through here, we can get rid of that minus a half. So what would that give us? Well, times it, you can also times by minus 2 essentially here. So if I times it by minus 2, it'll just cancel here and I'll just get z to the minus 3 over 2, like so, dz dx. We've got a half tan x times z to the minus a half. So if you times that by minus 2, well, the half is just going to cancel here, so all we're going to get left with is minus tan x times z to the half, or minus a half. So just to make it clear, the times in by minus 2 here, okay, to get this line of working. So I get tan x z to the minus a half, and then this side here, you times this by minus 2 as well. What would that give us? So minus 2 sec x times minus 2, so we're going to get positive 4 sec x. And then don't forget your z to the minus 3 over 2. Now we're getting closer. We've got a 4 sec x here. They've got 4 sec x, but obviously we've got this issue of this z to the minus 3 over 2. So how do we get rid of that? Nice and easy. I'm just going to divide through by z to the minus 3 over 2. So next line of working, we divide this by z to the minus 3 over 2. So do that. Well, that's just going to cancel there, so you're just going to get left with dz dx. We've got minus tan x, z to the minus a half. So if you've got z to the minus half divided by z to the minus 3 over 2. So just basic rules of indices, but just so it's clear what we're doing. Like so. Essentially this is minus a half plus 3 over 2, because you'd minus this minus 3 over 2. So what you just get left with is just z. So we can write that at the front, bring it to the front, minus z tan x, like so. And then this side here, dividing this as well by z to the minus 3 over 2, we're just going to get left with 4 sec x. And there we have it. That's exactly what we're asked to find for part A. So 5 marks for that. Hopefully nothing too crazy. Now let's have a go at solving this. So what we're going to do is we're going to use our transformed equations. That's the whole point of this. We transform this equation in something that, you know, makes life easier to work with. So if we just clear all this, we can have a go with it. So part B here. And even if you struggle to actually show part A, you still can have a go at solving part B, because we know what the differential equation is that we're working with. So if you look at your differential equation, hopefully it jumps out at you that for this question we actually need an integrating factor. So we need an integrating factor because it's just a first order differential equation. Makes life nice and easy. So we need integrating factor. Now sometimes you'll be able to just solve this using separation of variables, but for this one you do actually just need an integrating factor. So how do I get my integrating factor? Well, that's just simply going to be this expression here. So it's, remember, it's e to the integral, or the power of the integral here, of minus this expression here. So it's not the z, it's the minus tan x. So I can take the minus out to the front using linearity. So we get the integral of minus tan x dx. Well, this is just a standard integral here. This is equal now to e to the power of ln cos x. So it would be normally minus, because the minus here at the front of the integral makes it positive. So it's ln cos x. And again, just using the factor of e to the ln here, just cancels out. We just get left with cos x. Okay, so this should hopefully be pretty standard from your A-level core pure. So now we've got the integrating factor. We just multiply through by this integrating factor now. So what I've got here now is cos x dz dx. I have minus, so think about tan x, that's sin x over cos x. So if I've got cos x times sin x over cos x, the cos x's will just cancel, so I get left with z sin x. And then the other side, so that's 4 times 1 over cos x. So cos x times 4 over cos x, the cos x will just cancel again. So we get left with 4 on that side. Now, this stage here is probably the hardest kind of intuitive part of the question. You need to spot how we go from this line of working here, so if I call that 1, how do I go from 1 to my next line of working? Well, it is easy and it kind of looks. If you take a look at the expression we've got on the left hand side here, this is actually just the differential using the product rule. So this is d by dx of the product rule here of z cos x. Okay, so this is something that you will spot with just practice and more kind of experience with these questions. So this is just the differential of z cos x using the product rule, and that's obviously just equal to 4. And now just to make life easy, we can just integrate both sides. So if you integrate the differential here, they essentially cancel out. So we just get left with z cos x being equal to the integral of 4. Like so. So that's equal to the integral of 4 dx. So that's going to be equal to z cos x here is equal to 4x plus c. Don't forget your constant of integration here. And now at this stage here, all we want to do is work this out in terms of z here. So to get that, I just divide through by cos x. So that's 4x plus c divided by cos x. But we're not quite finished here. And the reason we're not quite finished is because we actually know that z is a substitution. And z is y to the minus 2. So, using that fact now, we can rewrite this. So we know where can I write this? Do it up here at the top. So using the fact that y is equal to z, so minus half, we can write this now as our general solution. Because we're, like it says here, we want to give y in terms of x. So obviously the final solution needs to be y equals. So what's that going to be? What's going to be y equals this expression here to the minus a half, because that's what we know the substitution is, y equals z to the minus a half. And then hopefully, this is relatively straightforward to just rewrite. So this is just the reciprocal here, and then obviously you take the square root. So y is going to be equal to the square root of cos x divided by 4x plus c. And there we have it. So that's our y there. So that's our final solution here for question 2. So like you see, these questions can be quite long, and there is just a few things you've got to be very careful of. So if you struggle with the differential equations chapter from the Core Pure textbook, make sure you need to, you kind of need to strengthen up on that. You'll find this chapter very difficult if you're, a bit weak with it. But let's have a look at the next question. Again, similar kind of idea here. We've got a substitution, and we want to show that differential equation given in this part here can be written as the differential here. So let's have a go. So like we always would, let's rearrange this, and we can also differentiate here. So with it being already in terms of u, we had to kind of escape having to rearrange it, but we will need to differentiate it. So this is u equals x plus y. Well, differentiate this here, du by dx. That's going to be equal to 1 plus, so differential of y here, so I'm going to get dy by dx. Okay. Well, we know dy by dx can be written as this expression here, x plus y plus 1 times x plus y minus 1. And if you notice, we have x plus y in both of those products there. And we know u is equal to x plus y. So we can actually rewrite this as dy by dx is equal to u plus 1 for my first bracket here, and then my second bracket will be u minus 1. Okay, so what we're also saying here as well is that du by dx is equal, or dy by dx I should say actually, is also equal to du by dx minus 1. So using this here, dy by dx is equal to du by dx minus 1. So now we kind of just piece everything together, and we just get this nice expression here that we're given. So how do we do that? Well, dy by dx, we know what that is here. So what we're saying here is that this is u plus 1 times u minus 1. So this can be simplified as a difference of 2 squares here. So that's u squared minus 1. And we actually know dy by dx is equal to du over dx minus 1. So if we do that, du over dx, which is just this here, minus 1, is equal to this expression, u squared minus 1. So add 1 to both sides, and all we get left with is the expression we need. So if you add 1 to both sides of this line of working here, we get this expression as required for part A. So as you can see, 3 marks for this, not quite as much work as the last one. So that's quite nice. We don't want to do as much work. So there we go. So that's part A done. Part B now. And again, this one is a simpler example, so it's always worth throwing it in. Just demonstrating this one, you can separate the variables for. So we've got du by dx is equal to u squared. Okay. Well, to solve this now, we just need to separate the variables. Okay, well, if you separate the variables here, nice and easy. My left-hand side will be in terms of u, this right-hand side will be in terms of x. So what am I going to get? Well, I'm simply just going to get here the integral of 1 over u squared du being equal to the integral of, it's essentially just dx. I'm going to write it as 1 dx here. Okay. Well, again, these are just standard integrals. The 1 over u squared here, that just works out to be minus 1 over u. We don't need a constant of integration for this one, but we do need it for this one here in terms of x. So integrating this, the integral of 1 is just x, but we have our constant of integration. So all we need to do now is get this in terms of u, and then we can use the fact that u is equal to x plus y here to get our general solution. So rearranging this in terms of u, I get minus 1 is equal to u lots of x plus c. So in other words, u is going to be equal to minus 1 divided by this here. Divided by x plus c. Okay. But we know u is equal to x plus y, so do it up here. So using u is equal to x plus y for this part now. Well, we know x plus y then is equal to minus 1 divided by x plus c. So remember, our general solution is in terms of y, so in other words, we just need to rearrange to get y equals. So therefore y is equal, simply just subtracting x off both sides. So that's going to give us minus 1 divided by x plus c, and then minus x. Nice and easy, job done there for 4 marks. So like you can see, it's much easier if you can just separate the variables compared to what you need in integrating factor, for example. But this is, kind of just an example, like we said, we're just separating variables. The final example here, so the next question, is taking a look where we've got a second order differential equation. So these are definitely the trickiest type. The reason for that is, especially because this textbook, this question's wrong for some reason. It should just be x squared here. X. So it's x and then the second derivative. So I'm not quite sure why it's x squared. Even in the mark, the solution bank at the back, it's given it as x and then the second derivative. If somebody knows why, or somebody knows kind of why this is the fault, then please do let me know. It seems to be a common issue amongst these textbooks that they're full of errors, so definitely not helpful if you actually revise it on your own, but let's have a go with it. So, part A, we've just got to show that this transformation of y equals z over x transforms the differential equation 1 into the differential equation 2 that's marked on the question. So for this one here, what I'm going to have to do is work out the first derivative of z with respect to x, and then work out the second derivative, because that's what we require here for equation 2. And we can also use the fact of the first and second derivative of z with respect to x to give us our derivatives for y with respect to x for the equation 1 here. So it might be easy if I kind of just demonstrate this. So remember, rearrange this to be in terms of z. So y is equal to z over x. So in other words, z is equal to xy. Okay, just times it across by x. Well, using this fact now, I can work out dz by dx and then the second derivative. Well, I am actually going to need the product rule for this. So let's just write that down. So u is just equal to x and then v is equal to y. So if you work out the derivative here for u, the first derivative, that'll just be a derivative of x, which is 1. And then the derivative of v, well, this is in terms of y now, it's just going to be implicit differentiation essentially here, which will just give me dy by dx. Okay, so I can now use the product rule to get dz by dx. So what will that be? Well, it's going to be x times dy by dx plus 1 times y. So in other words, just plus y. Okay, so that's the first part of this question. And again, we need the second derivative now before we can start transforming it. So let's just work that out as well. So again, I need the product rule because I've got x dy by dx. So u is x, and then v is dy by dx. But I mean, the rule's just kind of the same again. U prime, again, just 1. V prime here, again, it's just a second derivative of this, so d squared y by dx squared. So at this stage now, just apply product rule again. So this is going to be x lots of this plus 1 times the derivative here. So just the derivative. And then just be very, very careful. Don't forget your plus y here. So if you differentiate this y here, again, we'll get dy by dx. So at this point here, we've just got a load of derivatives everywhere. So how do we go from equation 1 to equation 2? So what we need to do here now is, given that equation 1's in terms of derivatives of y with respect to x, we need to write these equations here. So we call that equation A, well, differential equation A and differential equation B. I need to rearrange these to be in terms of y, or the derivative of y. So the first one here, so what I'm going to do is I'm using now, so we do the first, the second order first. So that's going to be x lots of d squared y by dx squared. So that's equal to, imagine you rearrange this, it's going to be the second order differential here of z minus 2 lots of this. Okay, so that's dx squared minus 2 dy by dx. Okay, so I'm just rearranging here. And the reason I'm rearranging it with this x in the front is because if you notice, and again, Edexcel have got it wrong, so let me just kind of run this out just so it's clear. Won't help if it's in white. This 2 here shouldn't be here, it should just be x. Okay, so it's x times d squared y by dx squared, which is why this works quite nicely. If this was x squared here, then this requires a bit more work, which doesn't work with the solution answers I've given, so I'm not quite sure how this error has gone through, but it has. So that's that part there. The first order then derivative, so that's going to be using this equation here, and again, I'm going to write that as x dy by dx, and you'll see why in a moment. So that's x dy by dx. That's equal to dz by dx minus y. Minus y. So we've got these now. Now we can transform it. So how do we do that? Well, imagine you substitute in here. So this part here, well, that's this. So I've got d squared z by dx squared minus 2 lots of dy by dx. What I would recommend doing here is expanding this part. So what you're going to get is 2 lots of dy by dx minus 4x dy by dx. And it might kind of jump out now why this works quite nicely. We've got 2 lots of dy by dx here, so we've got 2 lots of it. So like you can see already, these are just going to cancel, so that works quite nicely. We've also got minus 4 lots of x dy by dx. Well, x dy by dx is dz by dx minus y, so we just need to times this by 4. Or, sorry, minus 4. So that's minus 4 lots of dz by dx minus y, and then we also have minus 4y at the end here to make it equal to 0. So at this stage here now, we've done all the hard work. We just need to simplify. So can't do anything with this second order derivative here. That remains as it is. This minus 2 dy by dx plus 2y by dx, they're just going to cancel with each other. We've got minus 4 lots of the derivative here of z. And if you did minus 4 times minus y, you get plus 4y, but with minus 4y, so they just cancel. So all we get left with is this being equal to 0, exactly as we required there for the differential equation number 2. So therefore, equation 2 as required. So like you can see that there is a lot of work for that question. This is why the second order ones are much more of a nightmare. The method is usually just the same, just a lot more work involved. Thankfully for this question, B and C are really quite nice questions. So let's just get rid of all this. So if we get rid of all this here, we can just finish this off quite nicely. So part B, we want to find the general solution to differential equation 2, giving z as a function of x, and then part C is just a hence question to find the general solution to differential equation 1. So how would we do that? Well, we got the second order here of z, second derivative of z minus 4 lots of the first derivative is equal to 0. Now remember, when you're solving second order differential equations, we need to write this in terms of an auxiliary equation. So that's going to be m squared in this case, m squared minus 4m. And that's equal to 0. Okay. This stage here now, nice and easy. Like this is going to work out quite nicely. We factor an m out, so that's m lots of m minus 4 equals 0. So therefore we can just solve for m here quite nice. So m is either 0 or m is equal to 4. Okay, so therefore we can just obtain a general solution nice and easy here. So remember, just from your core pure knowledge, this shouldn't be too tricky. So the general solution. So we just use the fact that m is 0 and m is 4 here to get the general solution. And remember, it's in terms of z, so giving z as a function of x. So z is equal, so it's a, this is m to the 0, so it's just literally a, plus, so my next one is b. M is 4, so in this case it's e to the 4x. And that is literally all it is for part B. And then part C is just a one marker, so we shouldn't expect actually that much work. And the fact that it's a hence question means we're probably going to have to use a general solution. So let's consider this general solution here. So z equals a plus b e to the 4x. Well, if z is equal to xy, then what we can do is use this fact here. So xy is equal to a plus b e to the 4x. And remember, to get this general solution here, yep, for the differential equation 1 given, then we want it in terms of y. So how do we get it in terms of y? We just divide through by x. That's a over x plus b over x times e to the 4x there. And there we have it. So that's the final mark there for that question. So like you can see, part B and C, relatively straightforward. Part A just had quite a bit of work to do for it. But hopefully this video has helped. That brings us to the very end of the Further Pure 1 chapter. If there is anything else you'd like me to cover from Further Pure 1, or anything that needs a bit more detail, please just let me know down below and I'll get to it as soon as I can.